It's my pleasure to introduce our next speaker. Emre doesn't need any introduction. In fact, I would not want to, it's impossible to introduce him in a few minutes. But I'll just say, if you are a student of communication, I can guarantee you must have read his paper on capacity of multi-antenna Gaussian channel, which has more than 12,000 citations. He is recipient of IT Society Best Paper Award, recipient of EPFL Teaching Award, very illustrious researcher, and I'll give the stage to Emre. He's going to talk about Shannon's mathematical theory of communication.
Well, thank you very much for bearing with me while setting up. Hasn't happened to you a long time. Typically things connect much easier, but such is life. Well, I would first like to thank Adrish and all the IIT Kanpur faculty for having organized such a wonderful event and treating us so nicely on our arrival. We had students coming onto the airport picking us up. I'm not used to this kind of VIP treatment at all, so it's very pleasant indeed. So I would recommend everyone to come here and visit. This is the best place to be. My talk is maybe somewhat ambitiously titled. I mean, this is Shannon's paper, not mine. So who am I to be here to be presenting this particular topic? Well, in 1997, it was the year before the 50th anniversary of Shannon's 48 paper, Mathematical Communication. And Aaron Weiner, who was at Bell Labs at the time, I was at Bell Labs at the time also, he had the idea that we should have a Shannon Day at Bell Labs at the anniversary of the 50th publication, 50th year of the publication of the paper. So Aaron lined up luminaries to come and give talks for one day at Bell Labs. Unfortunately, he himself passed away before the event took place. In 1997, he passed away. But anyway, so at that time, we thought that of giving a copy of Shannon's paper to all the participants. Now, we said, okay, let's make a photocopy or something, but it looks extremely ugly. So at the end, we ended up typing the whole paper in LaTeX and using fonts which was as close to the original VSTJ publication as possible. I typed about half, and then one of our secretaries typed another half. And then I divided this whole paper into 10 parts, and then I found 10 colleagues. I gave 2 parts to each to read and do typo checking. Based on how many overlapping typos they found, we figured out that there must be so many more typos left, and then reread these things. It was a complicated process. But anyway, the story is that many of you probably have read Shannon's paper, but I have wrote it. So perhaps I can take some claim as to giving a talk with this type. So of course, what we're talking about is the Shannon's a mathematical theory of communication. This was published in the July and October issues of the Cloud System Technical Journal. It was republished again a number of times. There's, for example, the key papers in information theory, edited by Dave Slepian. It contains the exact text, but not quite, because it has the original paper at 2 section 21s. The number was wrong, so that was corrected and so forth. There are minor things. But the notable, perhaps, is the 1948 publication by the University of Illinois Press, with a preface by Warren Weaver. And the name has changed from the A mathematical theory to the mathematical theory within 1 year. I mean, perhaps justly so. I mean, I'm not sure if we can come up with a different, another mathematical communication will be, I think, hard to do. Now, Kanan already put up a slide with Shannon's 1949 paper, the mathematical of secrecy systems. However, this 49 paper was already published in 1945 in the classified literature. So people who know this, the secret systems comes in 45, AMTC comes 48, so perhaps Shannon did cryptography first, and then came to communications via cryptography. Apparently that's not the case. So the understanding is that this is not the case. Shannon had been working on the mathematical theory of communication for a much longer time, starting from the late 30s. And then his cryptography ideas was built upon the communication theory, and Slice said not vice versa. So if people come and say, 45, 49, 8, blah, 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 okay, no, that's not the case. Indeed, I mean, there's his letter. Shannon has a letter to Vannevar Bush. Vannevar Bush was Shannon's both master's thesis advisor and PhD thesis advisor. So he was a MIT professor, also I guess was the science advisor to Roosevelt in the time of the war. This is not the original letter retyped. So it says, Dear Dr. Bush, this is from 1939. Off and on, I've been working on analysis of some of the fundamental properties of general systems of transmission of intelligence, including telephony, radio, blah, blah. Practically, all systems of communications may be thrown in the following form. Okay. So now, you see already that there's parts of the diagram are already here, that you should have a completely general transformation that transforms your message, the word is not invented yet, to what is actually being sent. At that time, if you look at what is communications, you do very simple things. You take your signal f of t, you multiply it by a cosine and so forth. You do point-wise transforms, if you wish, in time. The idea you should take a look at this message in its entirety and do an operation on it, boom, and then to create thing to be sent as a function not only of the point-wise message in time, but the whole message in an ensemble is already here. Some other things are not here. For example, idea of noise, that the how is this f generated and so forth are not in this lecture. But I mean, this is give me a break. Right? He's trying a break. It's not, you're not there yet. And I think he really waited for a long time to develop the whole complete theory and then publish it at once. I mean, the paper, if you haven't read it, you should. It is remarkable that you sort of see, I don't know, Athena being formed complete in Zeus's mind and then appearing in one object. There's no, I mean, everything is there. Whatever we have done is just elaborations on what he has started. It's very remarkable. It's also written in a, I'll comment on this thing later on. It's a mathematical paper, but written in a very didactic style. You could make criticism of this, that he sacrificed maybe certain precision to make the paper accessible, but I think he made the right choices. I'll say more about these things later on too. I read the paper when I was undergraduate student. I was, I think, third year. Our communication courses at that time was heavily analog. I mean, we tried to compute the spectrum of FM modulated cosines and so on and so forth. Okay, yes, very nice, Bessel functions floating here and there everywhere, but and then when people want to talk about spectral efficiency, it became a complete mess because you don't understand what exactly are we talking about. At the time, I had a very good friend whose brother was studying information theory, and my friend kept talking about this brother of his. So I said, okay, what is this brother doing? So I checked out a copy of Shannon's paper from the library. I'm afraid I admit that I made an illegal photocopy of it. No copyrights. But I was fascinated by this thing. So when I applied to graduate school, I said, well, I'm interested in electromagnetics, microwaves, control theory, and so forth. But also I have read this thing, and it looks very fascinating. I'll introduce something, maybe communications too. And then, okay, so I became an information theorist mostly by accident. So Shannon starts with talking about what is information. What are we talking about? Okay. He says that the fundamental problem of communications is that we're producing at one point, either exactly or perhaps approximately, a message selected at some other point. Frequently, these messages might have meaning. This is irrelevant. Okay. Significant aspect is that the actual message is selected from a set of possible messages. The system must be designed to operate for each possible selection. Very remarkable statement. First of all, it says it's the choice that matters. Okay. So, if there's no choice, if you knew before you came to the auditorium what I was going to say, you shouldn't have come here. Because I'm not giving any information at all. You already knew what I was going to say. It's pointless to listen to me. The fact that you had uncertainty about what I was going to say, that I had the choice of giving this talk or something else or saying in a different way, is what makes you come here. And secondly, we see the origins of the network neutrality. Okay? Here. The meaning is irrelevant. Okay? So operator, the guy who designs a communication system, has to give equal treatment to all possible selections, okay, regardless of what the meaning of this message might be. Okay, so we have this already here. So the semantic aspects is something that has not been tackled. Maybe one can do a more general theory of communications which somehow involves these things too. But so far, I don't know of it. And then he starts with this, the coat of arms of information theory. Okay? This is what we put on our shields. So there's this information source, okay? And then there's the destination, okay? And there's the noise source, which corrupts whatever you're trying to do. And your thing that you're supposed to design as the engineer is these two boxes, okay? The transmitter and the receiver. So now, again, a very remarkable thing is that the Shannon models, this is important because you see, I mean, what is this object? It's the information source. It could be, okay, you read the temperature readings off the thermometer each day, or you listen to me, I'm producing something. I mean, Shannon could actually model this thing as saying, okay, yes, there is this biological process, okay, we have a brain operates in a certain way, it's going to produce these things in his mind, okay. That's a ridiculously complicated thing to do. So Shannon says, no, let's not do this. Let me model the information source as a probabilistic device. Okay? So that chooses among the possible messages, and a message is taken to be a sequence of things chosen probabilistically. So the information source is simply something that generates a stochastic process, okay? A succession of random choices. Now this is a model. Okay? So for example, you might not believe this at all. You might say, okay, look, I don't believe in probability. You might say that, okay, I mean, there is physics is what creates everything, so this model is just a convenience, and it is. Okay? After all, I mean, this is a theory paper. Shannon does not prove theorems about communication systems. Shannon proves theorems about models of communication systems. So I want to make this distinction. Sometimes models are wrong. Okay? So you can build a theory upon completely wrong models, and there will be a failure. Okay? So Shannon's success is that his models are successful. Okay? He has chosen the correct models who have stand the test of time. These were done in the 1940s. We still use them and maybe apply them. We actually build communication systems which are reliable, that they work. Okay? It could have another way around. All right. So now this model of probabilistic sources, it still remains non-intuitive to students. So when I think that the most difficulty I have in an information theory course is to convince the students in some gut level that, okay, this makes sense. And Shannon dedicates quite a bit of time in the paper. If you read this thing, there are pages and pages of examples and explanations as to why this model might make sense. So Shannon spends himself quite a bit of time. And he concludes saying, it appears, I mean, you see the modesty of his claims here. It appears then that a sufficiently complex stochastic process will give a satisfactory representation of a discrete source. He makes no claim that all sources are this. There's no such thing. He says, okay, this is a model. Okay, that's what I take it to be. Very important. I mean, he's very cognizant of the limitations of mathematical theories. This is not physics. And his running example in the paper are these class of what is called Markov sources. Okay? And the nth order Markov source, the successive symbols are generated one by one. And the statistics of the next letter that you produce depends on the most recent things that you have previously generated. The reason I spent so much time trying to make the computer work was that I had written a program which was generating these sources with higher and higher order Markov things. By giving you an example based on Pride and Prejudice, you feed Pride and Prejudice to the machine, it compiles the statistics and then generates a second order Markov source based on the statistics of Pride and Prejudice, and the third one, fourth one. You see that, I mean, you get something resembling fairly decent English text after a few orders. In the meantime, this L most recently generated letters we call to be the state of the source at the current time. Okay. Online example, sorry, we skipped. So now, more generally, what Shannon has in mind appears to be the following. The source has an internal state. Okay, call this, the state set of possible states is finite. And the S sub I is the state of the source at time I. Okay? If the source of the state at time I happens to be little s, then generate the letter, next letter ui, from an alphabet u by some probability log p of u given s, okay? Independently of whatever you have done in the past. Okay? So the state captures all the past. So whatever in the future, influence in the future of the past is only through this state that the machine deserves. Okay? The next state S is determined by the current state S and the thing that you just generated. Okay? And then furthermore, this is not stated in the Shannon's paper, it's necessary for his computations to work out correctly, that if you know the current state and the next one, you can tell me what the letter is to. Okay? This ends up being necessary for things to work. So the first three of these things make this thing make this SI into a Markov process. Okay? And the Shannon further assumes that this process is stationary and ergodic. Okay? If you don't know these things, it's irrelevant to the discussion. Okay? Now, he then brings about how do you quantify making a choice? Because we said that given the current state, you're going to choose the next letter based on some distribution. And you want to quantify how much choice is there numerically. Okay? So when one of k items is chosen, little k item with probability p sub little k, how much choice is actually there? And the Shannon proposes numerical quantity called entropy, given by this famous p log p formula, as the natural answer. He motivates this thing a number of ways, and then, of course, the answer generalizes to making two choices. If you're choosing not just u, but u and the v, you just simply replace p of u by p of u v. Conditional choices, how much choice they're choosing v given u, and so forth. There is natural generalizations. Okay? And then Shannon motivates this thing by an axiomatic approach. He lists certain desirable properties of this numerical quantity based on things. For example, independent choices uv, entropy should add. H of the uv, if you're independent, should be hu plus hv. Few other choices, few other desirable properties, and then he says that this is the only possible formula which will satisfy the desirable properties. Personally, I don't like this. Okay? I'm not too keen on axiomatic approaches to defining things, because, I mean, how do you know that you have chosen the right desirable properties? But the better motivation comes from an operational meaning of entropy. Now, suppose this letters u1, u2, etc. are produced by a source which of the kind that we just described, with internal states S1, S2, and then that this entropy of the source is then going to be given by this h of the u given s, is going to be, under the assumption that we just made, is the entropy of the source. Okay? Then this is what happens. Shannon proves this, okay, in the paper. You give me some small epsilon, and you give me some length n. And then within the n-letter sequences, so these are all the possible n-letter sequences. I put a dot for each of them. Okay? There are many dots here, one for each element of u sub n. If u were ternary, there are 3 to the n dots in this picture. Okay. Within this one, there is a subset, these red dots. All right? These red dots, the set of this number of these red dots is not very big. Okay? So instead of being cardinal to u to the power n, it is only of this approximately 2 to the n times this entropy size red dots. Okay? All right? So there are much fewer red dots than the all possible dots. You can distinguish red from gray, right? There's red, blue, red, green color blindness, but I haven't heard of any green red. I mean, it's a gray red I have not heard of. Nevertheless, these red dots, if I plotted these points by weighing them with their probabilities, okay? Each of these dots is a probability of being produced, okay? Then they contain almost all the probability. So the probability of the source producing something in these, among these red dots is very close to 1. So this small set contains all the probability. Okay? So consequently, what you can do is you can represent all except a small probability remaining the gray dots by using only nh bits. So n-letter message sequences, almost all of them, probabilistically, can be represented by nh bits. Now furthermore, you might say, well, maybe this was an overkill. Perhaps I could find a smaller set which still contains all the probability. Maybe I could find a set A, okay, which contains some decent amount of probability, non-negligible probability, bigger than epsilon probability, that set has to have at least size 2 to the nh. You cannot find high probability sets or significant probability sets with smaller than 2 to the nh size. So consequently, these nh bits are in fact necessary to represent the source. Okay? So entropy is not just some axiomatic object that you derive from axiomatic properties, but in fact it's an operational concept. The h bits per letter is necessary and sufficient to represent the source. Okay? So now, Shannon, having shown that this h has this interpretation of the necessary and sufficient number of bits that you need to use to represent the source, he also gives a explicit method. Okay? It's not just a pure theory paper. Here's the existential results. Okay? I prove to you that h is necessary and sufficient. He actually comes up with a particular method of data compression, which uses exactly, well, not or close enough to nh bits. Shannon's method represents, that he described in the paper, represents a source sequence of length n using a variable number of bits. So it represents not just the red ones, but also the gray ones. Okay? But on the average, it requires less than nh plus 1 bits per letter, so bits in total. So per letter, it is h plus 1 over n. If n is big enough, it is h. Okay? Now, the Shannon's method is a precursor to what is now known as Huffman coding, which is the best possible method of compression using variable length code. And it also contains the essence of modern arithmetic coding. Shannon's method, if you just look at this thing carefully, you'll discover arithmetic coding naturally. And that's the sort of the gold standard, I suppose, if you're doing source coding, knowing the source statistics. I'll say a few words today about the modeling issue later on. Now that we have dispensed of this data compression, Shannon goes into talking about transmission of information. So now, Shannon's first model, because he'll talk about more complicated models later on, of a communication medium is discrete in time and value. Okay? So it's a box. Okay? It's a probabilistic box. It accepts a sequence of letters, x1, x2, x3 in time. Each of these x's, they come from finite alphabets, maybe each binary, for example. Each of the x size is either 0 or 1, okay, for example. It also produces letters at the output, y1, y2, so forth, okay? Again, from finite alphabet. Y's might be binary too, okay? Or something else, but they're discrete. Okay? And then these y's are connected to these x's probabilistically. So the y's is not some not necessarily deterministic function, but there's some probability involved. Okay? Now this kind of model, in contrast to the model of the information source, the students find this much more natural, because I guess the idea that the things are noisy in transmission is much more acceptable to the students than the information being generated in some probabilistic manner. So that the noise is stochastically motivated is usually fine. All right. So now Shannon's chooses to model this stochastic linear channel with the help of a hidden channel state. Okay? So that allows the channel to keep some memory of the past, okay? And some probability kernel, this p of the y and the s, given x and the s. So it says the following: if the channel is currently in some state s, and you feed it the input little x, then this gives the probability of being the next state being s prime, and the output of the channel being y. Okay? So this is the generation of the output symbols and the next state based on the input symbol, and the current state is governed by this particular rule. Okay? And this is again independently of whatever has happened in the past once this S is given. Again, the channel state S summarizes everything which has happened in the past to the channel. Okay? All right. So if you simplify this, saying suppose only a single state, so there's these S's can take only a single value, then you get what is known as the discrete memory of this channel. That's Shannon's models also capture that. Okay. All right. So now we're supposed to design this transmitter receiver to make communication reliable. Okay. So now what we say is that given the information source, whose entropy now we know, okay, and given this communication channel, which is captured by this, we say that reliable communication is possible, that you can send this source reliably to the destination, if for every epsilon you give me, whatever, however small it might be, I can design these two red boxes such that the probability of a source symbol arriving here in error, different than what is being produced, is less than epsilon. So you asked me to design a system with error probability 0.1, I should be able to come up with these two boxes. If you ask me, I'm not happy with 10% errors, design me something for 1% errors, again I should come up with maybe a different, these red boxes that will do that. Okay. If you say, no, I'll actually more reliability, I want 10 to the minus 12, I should still be able to do this, and so forth. Okay. So if I can do the sequence of the designs, no matter what your request is, I say that it is possible to communicate the source reliably. That's the notion of reliability Shannon has. Okay. And then Shannon defines, he writes a formula, okay? It says the capacity is the maximum difference between the entropy of the input to the channel, minus the input condition and the output. He doesn't quite say what exactly this is, because he writes simply h of x minus h of x given y. Okay? All right? And then he says maximize this. It's not clear what he means. Am I supposed to look at these things in blocks, take the difference, divide by n, and then take the supremum over all possible input distributions of these blocks, and then the limit as n goes to infinity? Does this limit even exist? I don't know, generally not. Okay. Does it mean something like this? Okay, lim inf of this thing, maybe, because the limit may not exist. Okay. Does it mean, okay, take the all possible infinitely long stochastic processes, take the lim inf of this? Okay, or do you mean, okay, this is actually a joke because this is in fact the true answer in some sense, as the probabilistic limit inf, the supreme of this, and so on and so forth. It's not obvious what he means. Okay? However, indeed, in fact, the Shannon's channel model that you just described is too general. So his formula will not be correct. Okay? This formula, in fact, will not give the correct channel capacity in the Shannon's notion of model of the communication channels. Okay? However, okay, if you just put some small regularity conditions on his model, such as being that the state diagram is indecomposable and so on, and his proof text will give right answers. Okay? But for this discussion, let me just assume that we have a discrete memoryless channel, a single state channel, okay? For which case all these formulas I wrote are the same. Okay? They give the same answer no matter what, and in fact becomes a single letter, namely that you just maximize in a single letter wise the difference between the entropy of the x and the entropy x given y, x being the input to the channel, y being the output to the channel. Okay? Now Shannon, by the way, never uses mutual information. So in the Shannon paper, you never see the I of xy is not there. Mutual information is a concept coined by Robert Fano later on, because this difference of entropy and the condition appears so often in information theory that he figured it should have a name and called it mutual information. So even the terminology is due to Fano, not to Shannon. All right. So Shannon shows that, so now that he had defined a C, or computed the C, Shannon proves the following theorem, that if you have a source of entropy H and a channel of capacity C, then reliable communication is possible if and only if H is less than C. Okay? The source should produce less entropy than the channel can carry. Okay? That's it. Okay? If H is bigger than C, you cannot make these designs that are reliability. If H is less or equal to C, you can. Okay? Some people complain about the equality sign. It is there. So it is H equal to C is fine. You can still do reliable communication. Okay. Now, remember that in the source coding case, I said that the Shannon finds the entropy and then relates to an operational meaning of compressing sources to H bits per letter, and he does so by constructive methods. He gives an explicit algorithm, a method to say how you can compress to entropy, Shannon coding, which then was as I said, the precursor for Huffman coding and arithmetic coding. For the case of channel coding, he gives no such constructive design because he doesn't know it. Okay? In fact, it took us, 5 decades or more to come up with constructive methods to in fact do so. Nevertheless, he comes up with an ingenious method of what is called now random coding. Cannon alluded to this in his talk. He does it by what is called a probabilistic method. Okay? You show the existence of something by making a random experiment, and then to show that the probability that this experiment will succeed is bigger than 0. Consequently, there must exist some point which satisfies the constraints of the problem. Okay. So now he does the following thing. He says, consider a auxiliary memoryless source. Okay. So nothing to do with the source itself, that attains this maximization definition of C. Remember, this capacity had this maximization over input of distributions on the x of hx minus h of x given y. Take a source, IID source, memoryless source, which is distributed like this x, which attains it, and then consider sending this IID sequence of letters over the memoryless channel that you have. Okay? Then we get the pairs x1, y1, x2, y2, x3, y3, xn, yn. These will be an IID sequence of pairs with entropy h of xy. Okay? So, remember this picture of these gray dots and the red dots. Okay? So there are 2 to the n of xy typical xn, yn pairs, the red ones. There are 2 to the n of hx typical xn's, 2 to the n of h of xy typical yn's, and so forth. And then the picture is like follows. It's exactly from Shannon's paper, figure 10. Okay? We had figure 1 with this block diagram. This is figure 10 in Shannon's paper. So there are these 2 to the n hx, h of x high probable messages, 2 to the n hy high probable received signals. Each of these things are connected to 2 to the n h of y given x possible effects, and each of these things have 2 to the n of x given y possible causes. Then Shannon says, just randomly pick 2 to the nr dots from this right column, okay? And then, upon observing this y, the receiver is going to pick one of these things that you picked as being the reasonable cause. Okay? Now, if r is less than c, what you'll find is that only going to be one reasonable cause, so you'll find a correct message. Okay? That's this condition that this r is less than h of x and h of xy guarantees that among the things that you picked, among these things here, only one of them will fall into here, so you know the correct answer. Okay, that's Shannon's proof. So now, Shannon shows that he gives a converse too. If h is more than c, okay, then no matter how you design the Shannon receiver, you will have this uncertainty that the conditional entropy of what is sent, given the thing that you observe at the receiver, is going to be some non-negative number. Okay? So now, he doesn't talk about error probability at all at this moment. Okay? So we typically these days in information theory courses, we go from this statement to the fact that you are not reliable by using something called Fano's inequality. At the time of Shannon's paper, there is no such thing. Fano's inequality is about 5 years later. Okay? However, okay, if you read Shannon's paper further on, you will see that in fact he has connected. He has in fact Fano's inequality in fact already there in some sense hidden. In his chapter 5 of his paper, which Canan already put the first title of it, the rate distortion part of this paper is, in fact, will show you that this condition will ensure that the reliable condition is not possible, that this will give an error probability bound. All right. Shannon even states what is called a strong converse, namely that not only is the error probability bounded away from 0, and in fact the error goes to 1, is already claimed in Shannon's paper without proof. Okay? He says it's true. Okay? You can prove it later on, but he states it without proof. So now, myself, I have a preference for proving converses on symbol error probability, because this kind of strong converse saying that you'll make an error in the block, it is fine, but I don't like it very much. Okay? So after all, somebody who's using your communication system does not know that you're using block codes or not. Okay? So he has no notion of block, at least your notion of block and his notion might be very different. So I don't like these proving strong converses and leaving at that. One has to prove, I think, a converse with the symbol error probabilities to start with. Anyway, now there are questions about modeling. Now, both for sources and channels, one can question Shannon's choices, okay? Whether the models are appropriate, and if so, can you really know the model? Because to assume that there's a probabilistic source and assume that there's a stochastic channel is probably fine. But to insist that before you make this design, you have precise knowledge of these stochastic models might be unrealistic. So at this moment, on the question of are models appropriate, I mean, do we really think that Shannon's choices of modeling the sources as probabilistically generated and the channels as being noise governed by stochastic processes, are these appropriate? I think at this moment there is no question about them. Okay? So they have stood the test of time. We built things, they work fine. Okay? Now, however, one should note that Shannon's techniques, if you take a look at how have we proved that reliable communication is possible, those proofs depend crucially on the fact that not only that is there such a probabilistic model, but you know at the design time what the model is. What is the P of y given x? Somebody has given you that you have a binary symmetric channel with crossover for 0.15, as in Canan's example. If I don't know that, if I don't know that the channel has crossover for 0.15, but maybe it is between 0.15 and 0.78 or whatever, then I may not be able to design the communication system. Okay? Or to do a source compressor, okay, compress the source, I need to know the precise statistics of each possible P of x. I need to know them. At least on Shannon's paper, there's proof that the things exist depend crucially on these things. Now, I suspect that Shannon's instincts, he's a good engineer. He's not some mathematician of the, he picked up from the function analysis department from the math department. Okay. He actually is an engineer, so he probably knew that slightly imperfect knowledge of the model will only slightly diminish the achievability of these compression and transmission claims that he's making. Okay. Nevertheless, I mean, it is a theoretical necessity to develop stronger theorems which talk about universal compression and coding. Okay. So you have to do them, otherwise the theory is void. Okay. Because you cannot, in engineering discipline, you cannot start with something saying that given the source and the channel, I can design. Okay. Because there is never a given source and the channel. You just have a physical object, okay, which may or may not be governed by the laws that you think it is being governed by. Okay? So there is no such given thing. You have to assume that your models might be inaccurate. All right. Now, Shannon now goes on, from this point on, to discuss somewhat more complicated things, such as everything was discrete. He talked about waveforms. Okay? He dismisses the continuity of time very quickly. Okay? So he immediately says, I'm going to use a sampling theorem to discretize time. Okay? Boom, I'm going to take in a length of time capital T, if my singles are bandlimited to single-sided bandwidth W, I'm going to take just 2 NWT samples and I'm done. Okay? Well, I mean, not quite. This is intuitively plausible, okay? But this requires some effort because you can construct with very strange examples in which while things work in the infinite time domain, if you take the samples from minus and plus infinity, you can reconstruct. But if you only give me the samples from a given time interval, I may not be able to construct the signal inside time interval at all. Okay? So this requires some extra work. It caused lots of confusion. Okay? There were papers claiming that the Shannon's capacity formula for the Gaussian channel was wrong, blah, blah, so forth. But no, he's right, but it took us a while to fix it. Okay? And then he talks about how to generalize entropy to continuous sources. He suggests this. Okay? This ends up being a much uglier object than the discrete entropy. Okay? So in particular, this continuous entropy or differential entropy is not invariant under one-to-one transformations of the random variable x. Okay? However, the difference, which Fano later called mutual information, is invariant. Okay? Unfortunately, all the theorems that depend on these things remain whole. Okay? Shannon develops a nice theory as to how to deal with these kinds of continuous valued inputs and the outputs of the channels. He spends quite a bit of time for the Gaussian case, and he shows, for example, that among all random variables of a given second moment, the Gaussian distribution has largest entropy of this particular value. And then he makes a remarkable claim. Okay, so I'm sorry that this is technical, but I have to put this thing up. He says that suppose there are two independent random variables. They're not Gaussian, or may not be Gaussian, not necessarily Gaussian. Okay. But suppose they have this much entropy. So the entropies is half log 2 pi e n1 and half log 2 pi e n2. This is just, I mean, you can solve n1 as being taking multiplied entropy by 2 exponentially divided by 2 pi e. So it's just a coordinate to represent this. And then he says that the entropy of the sum of these two random variables, they're independent, remember, is at least this much. He gives a proof Okay? In appendix whatever, appendix 4 or something. Okay? He gives a proof. You look at the proof makes no sense. Okay? So the proof is completely wrong. Shannon's proof is wrong. Not only it is wrong, that proof cannot be fixed. Okay? Shannon has other proofs which are not completely, not all the I's are dotted, not all the T's are crossed, but they can be fixed by the same logic of the proof. You don't need to introduce any new ideas. Okay? This one, you can't fix in that way. To prove this particular statement, which is true, okay? I mean, amazingly enough, I mean, typically if I make a statement and my proof is wrong, my theorem is typically wrong too. Okay? In Shannon's case, okay, he makes a statement, gives a wrong proof, but the statement is still true. So, I mean, I think this, if anything, is a testament to Shannon's himself. Okay? He knows what is correct. Without even having a correct proof of it, he knows what is right anyway. Okay? So he senses the truth in a very deep way, which I cannot really explain. Okay? So this is what is known as entropy power inequality. His proof took maybe another, about, I think Stam was the first one, 59. So it took about 11 years to come up with a correct proof of this, based on completely different ideas. Okay? So it's the proof of this statement requires introduction of different ideas to the thing. You cannot prove it by the methods that Shannon suggested. It's remarkable. And then Shannon talks about waveform channels. He puts the cost constraints and the power constraint and so on and so forth. And then he pays attention to the channels with a Gaussian noise, okay, with a second moment power constraint. And he gives the capacity as being this log, W log 1 plus SNR formula. In fact, I mean, this formula, in a sense, is very unfortunate that the formula is so simple. Because lots of people who know nothing about information theory, they know this formula. And they think this is generally true. Okay, so no matter what channel you give them, they say, oh, the capacity is log 1 SNR. You say, no, okay, it is not log 1, it is not the correct formula for every possible channel. It is only true for this Gaussian channel with the second moment power, etc. But the fact that the formula is so simple makes a whole bunch of non-specialists think that they understand everything. It's very irritating sometimes. Okay. All right. So now, the last topic in this paper, I'm really going through the paper chapter by chapter. Okay? The last one is about rate distortion theory, which can unput in some detail. Lossy compression. How many bits are required to quantize a source U if we're willing to tolerate some distortion in its reconstruction? Okay? So now Shannon motivates the question from the case of the continuous value sources, which will otherwise require an infinite number of bits to represent accurately anyway, so you have to do something. So no matter what you do, you have to tolerate distortion, so you might as well consider it from the beginning. Okay? And it devotes a lot of time, purely philosophical, as to why you should measure distortion by this expected value. Okay? He says that any kind of fidelity measure, if it makes any sense at all, has to be of this form. That you should have some function rho which measures the penalty for representing a letter U by the letter V. Okay? Then you should compute this rho of this UV and takes the expectation over the distribution of these source letters. He says this is the only meaningful way to measure fidelity, okay, or accuracy. And then he then says, okay, suppose we are given information source. Suppose we are given a distortion measure. Somebody gives us these things. Suppose somebody gives us that I can tolerate this much distortion. How many bits do I need? Okay? He actually has an even more complicated question. And the communication channel, the capacity C, can we design these red boxes that we've been designing all the time so that the reconstruction is within this distortion level nu? Okay? And the Shannon says the answer is yes, if the capacity is bigger than some what is called rate distortion function, for which he gives a formula similar to the capacity formula, with the same caveats as I made. Okay? So what he means by h of u minus h of u given v, am I supposed to take blocks, divide by n, take a limb or something, or it is not clear. But he says just difference between h and h of u given v, maximize it and so forth. Yes, so minimize it and so forth. Okay. All right. Okay. So, however, if you have memoryless source, everything is fine. Okay? And the Shannon gives examples. Notably, when for the Gaussian cases, he computes the rate distortion formula for the Gaussian channel, or Gaussian source with a squared error distortion. Now, Shannon's proof has the same logic. This random coding approach is also used here, okay? And subject to the same caveats that It's not completely true unless you assume some regularity conditions and so forth, but it is, contains all the correct ideas and all the essential ideas. Very strangely, maybe importantly, while proving this theorem, Shan also establishes what it calls now the separation theorem. He doesn't remark on this at all. No mention of the separation is made when you read the paper, but it's an architectural principle. Okay? So he says that when you design these red boxes that take a source and map it to the channel, you can do it in a modular way. Okay? You take the transmitter, you break it into two boxes. Okay? The first box gets to see the message. Okay? The first box is designed, okay, with the knowledge of the following things. It knows only about the source distribution. It knows only about distortion metric, and knows about the fidelity criterion. This first box is designed with no knowledge of the channel. Okay? It's only designed by the knowledge of the source. The second box, similarly, is designed only by the knowledge of the channel itself. Okay? Only by what is the channel statistics. And these two designs can be made separately and then glued together here, okay, by a universal interface, say bits. Okay? So this first box outputs bits or any other digital format that you would like. Okay? So consequently, these bit interface here is a universal interface, okay, and can be done. So the fact that you make this design this particular way is done without any loss of performance. Okay? So whatever you could have done by making this design jointly to make this map from a message to the signal in an arbitrary way, versus making this design like this, making design in this modular way, causes no loss of efficiency. Okay? So this is in fact what distinguishes digital from analog communications. In analog systems, you take your analog signal and you modulate some way, somehow. You take your waveform that my sound makes, you multiply by cosine, and then you send this thing. Okay? So purely analog conversion. The fact that you have this digital interface here is what makes the modern systems, the digital communication systems, not because all systems at the end, they work with physical signals. Okay? You don't never send bits across any channel. There is no physical channel which accepts an abstract quantity as a 0 or a 1. A 0 or 1 are mathematical concepts. They don't exist. Right? So as it's an abstraction of physical reality. So I make a few remarks and then conclude. Okay? So this is, I mean, a complete end-to-end theory emerges in one single paper, boom, like this. Okay? So, I mean, you read this paper every so often. It's a good idea to do this. Okay? So it's like going to Sunday school. Okay, you go through this. Okay? And then I think every few months one should sort of take a look at the paper and then read through a little bit. It never fails to be amazed. You say, wow, I didn't realize this particular point of this paper. It's just saying something very, very interesting. Okay? And then, I mean, I don't see very often a complete research field emerging in one shot, in the mind of one man, in one paper. It's very rare. Maybe Newton's Principia is maybe a good analog of this. Okay? You have full theory of gravitation and planetary motion, boom, shows up. Okay? In a similar sense, I guess Shannon's paper has the same influence on us as Newton's on physics. Okay? And despite the heavily mathematical nature, and I apologize for going into some details of mathematics in this talk, maybe it was inappropriate, but anyway, it is done. The paper is extremely didactic, okay? So it can be read by a undergraduate, not too advanced. Okay? And you hear lots of criticism saying that, oh, okay, Shannon did not dot this I, did not cross this T, so the paper is wrong, blah, blah. Completely misses the point. Okay? So first of all, the ideas of Shannon are correct. Whenever he proves something, you can turn this proof with a few epsilons and deltas to a complete exact proof, no problem at all, because the ideas are correct. Except for this one exception that I mentioned for this entropy power inequality, but even there he's right. It's remarkable. Furthermore, I mean, if Shannon had written this paper in a fully rigorous way, I think it would have not been read at all. Okay? So I think it would have no impact whatsoever. Okay? And also, to do this thing completely correctly would have required 10 more years. I mean, Shannon had been working on this for 1939 onwards. Okay? It took him 10 years to figure out this publication. If he had to wait until he crossed all the I's and the T's, the paper would have been 10 times longer. Okay? It would have come a decade too late. and then would have been unreadable by most. Okay? So I think it's just the right paper to write at that time that he wrote it. So maybe I should just make one more remark and then really finish. Of course, any mathematical theory is concerned by mathematical models of reality, okay? Not the reality itself. Okay? So one should make sure that when you develop a theory like this in a discipline such as communications or any other engineering discipline, you have to make a trade-off. If your models are too accurate, if you, for example, try to model the information source by first constructing a accurate model of the brain, for example, okay, and then deciding what do humans say in their speech or writing, okay, then, I mean, this would be something which is accurate, but you won't be able to analyze it, you won't understand it, you'll have no intuition from this. But if you're too simple, if you ignore too many parts of the physical reality, then you come up with a model which you can probably easily understand, but will say nothing about anything. So it's one of these trade-offs that you have to do. And the Shannon's theory of mathematics, AMTC, okay, but really has no parallel in the engineering world in the sense of finding the right level of abstraction. Okay? So with that, I'll conclude. Thank you very much.
Okay, let's thank him again for a very wonderful talk.
Thank you so much. It's really unappreciated.
Peacocks are all across the country.
They're wonderful animals. Thank you very much indeed. Very kind.
Our sponsor, Springer.
Thank you. Thank you so much. This was truly necessary. Thank you very much.